Hey everyone, in this lesson we are going to solve the problem 5 on the collection of problems about push-down automata. In this problem 5, they ask us to write the deterministic uniquely accepting PDA push-down automata to recognize this language, which is this one that is given. Yes, this is the language over the words over the alphabet A and B, such that the number of A's is greater or equal to the number of B's. Yes. So if I want a given word to be accepted, then this word must have more A's than B's or the same amount of A's and B's. Yes. So here we have a brief description of the statement. Yes. Such that the number of occurrences of A is greater than or equal to the number of occurrences of B. Yes. So if I have a word that in this word we have more B's than A's, then this word will not be an accepted word for this language. Yeah. So before jumping into the construction of this PDA, we will first see some instances of words that belong to this language, then some instances of words that don't belong to this language, so that we fully understand this language. So the language that is given is this one, the words over the alphabet A and B, such that the number of A's is greater or equal than the number of B's. Yeah. So now, yes, consider this word, the word AB, B, A, A. Now, is this word a accepted word for this language? Well, we can count how many A's and how many B's we have. We see that in this word we have a total of 3 A's and we have 2 B's, right? So, since we know that 3 is greater or equal than 2, which is basically saying that the number of A's is greater or equal than the number of B's, then the condition is met, yes? And since this condition is verified, then we can come to the conclusion that this word belongs to this language, yes? So it is an accepting word. Okay, so now consider the word B, B, A, B, A, yeah? And let's break down this word. Is this word a valid word for this language? Well, let's count how many B's we have, for instance. Well, we have a total of 3 B's. How many A's? We can see that we have also a number of 3 A's. So, since they have the same amount, the condition that the number of A's is greater or equal to the number of B's is also met. So in this case, we have met that they are equal. So we come to the conclusion, again, that this word belongs to the language. Yeah. Okay, so before jumping onto the words that do not belong to this language, we are going to see the last instance of this word. Consider this word, the word empty word. Remember that we can represent the empty word with the lambda. Yes, this lambda in here represents the empty word. So in this word we have no symbol. Yes, we have 0 symbols in this word. So this is the same, for instance, as having A power to the 0 concatenated with B to the 0, or B to the 0 concatenated with A to the 0. Okay? We have no symbol. So since we have in this empty word a total number of A's of 0 and a total number of B's of 0, yes, since they have the same amount, then the condition of the A's being greater or equal than the B's is also satisfied. Yeah, because they have the same amount, they have 0. So this word, we can come to the conclusion that the empty word is also a valid word, a accepted word for this language. So our PDA, right, or push-down automata must accept this word as a valid word in this equation. And remember, whenever we have that the empty word is a valid word, then the initial state, since the empty word, okay, is where the initial state begins, so the initial state will also be a accepting state in this automata. Yes, this is some criteria that we can come to the conclusion with these details. So let's continue with more instances of words Now let's consider the word BA, B. So, is this word a valid word? Well, let's count how many A's and how many B's we have if this condition is met. We see that we have a total of 3 B's and we have only 1 A. Yeah. So, is this true? The number of A's is greater or equal than the number of B's? Is this true? Well, it is not true, right? This is false because we see that 1 is not greater or equal than 3. Yes? So, since the condition is not met, is not satisfied, then we come to the conclusion that this word does not belong to the language. Yes? So, our PDA, or push-down automata, mustn't accept this word. Yes? It should be an invalid word in the execution of this push-down automata. Let's consider now this other word, the word A, B, 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 A, B. Okay? So if we count up how many A's and how many B's we have in here now, we see that we have a total of 4 B's, right? And a total of 2 A's. So since the number of B's is greater than the number of A's, so basically this condition of this statement, yes, is not met. Okay, since this condition is not satisfied, then we come to the conclusion that this word does not belong to the language cell. Yes, and that's the basis of this language. So once we have understood fully how this language works and how this language will accept words, basically which words this language accept and which words this language does not accept, let's start now with the construction of this push-down automata. So the idea in here is that we have to verify that whenever we have a given subword of my word, imagine that I have my word W. Yes, this is a sequence of symbols. So let the subword be this part. Let's call it the W prime. Yeah, I have to verify if I am in the state where this is met or this is not met. So I will have two states in here. Why? The first one is the one where I have this condition satisfied, and the other, okay, the other state is for basically saying that this condition, yes, is not satisfied. Okay, so important, two states. One, the condition is satisfied. In the other, the condition is not satisfied. Okay, so in here, let's just call it the state. We can call it any name, the state S, and then the state B. Okay, in the state S, the condition is satisfied. In the state B, the condition is not satisfied. Okay, this is the initial state. Since we have seen that lambda belongs to this language, okay, so basically in here we can see that satisfied condition, and in the state B, not satisfied. Yes, we also have to remember the mechanism, yes, and the behavior of any PDA, of any push-down automata. Okay, we must remember that in any push-down automata, we have the stack, where initially the top of the stack is the Z, which is the neutral element. Okay, initially we have Z as the top of the stack. Okay, so how will this automata work and how will this automata behave? Yeah, so the idea is that whenever we read a given symbol A, we have to push the variable A, and whenever we read a symbol B, right, what do I have to do? Well, I have to push a symbol B. Okay, but I will pop the variable A or the variable B if and only if I have A as the top of the stack. So we will see it now. Okay, let's just start this building. So we initially have the state S. We can represent this state to be the initial one with this arrow. Yes, we also have seen that the lambda belongs to this language, so it will be an accepting state. Since the empty word is an accepting state, then the initial state is also an ending state. We represent the state to be an ending state with this double circle in the node. Then I have the state B, where the condition is not satisfied. Since in this state the condition is not satisfied, then it's trivial to know that this state will not be an ending state. It will be not an accepting state. Okay? So let's start. What happens at first where I have Z as the top of the stack? Okay? Imagine, okay, I have Z as the top of the stack. Then I read the A. If I read the A, I have to push the A, the variable A. But I do not want to pop the Z. And remember, whenever we do a transition in a pushdown automata, the default action, okay, in a automatic way, this will always be true, is that the top element will be popped. So we can avoid, okay, this. We can avoid this to be popped. How? Well, we can push it again. So we basically push the Z again, so it doesn't get popped, okay? And formally, it will get popped, but since it will get pushed again, nothing will be modified. And then we push the new A consequence of reading this A. And the same goes if I have Z at the top of the stack, I read the symbol B, then I have to push the Z so it doesn't get popped, and I push the B. Yes, like so. Now, what happens, yes, in the state where we always have the condition that we need. So what's the condition? We need to have more A's than B's. So basically, in this state, okay, we must not add the ZA. So the ZA won't be valid in here. So basically, we will delete this and say, okay, in the state S is the condition where this is satisfied. I will have more A's or the same amount of A's and B's. So now if I read the A, I just come again to the same state. You understand? So this is evident since if I have more A's than B's, the condition will be satisfied, so I must stay in the same state as, like so. And the same goes if I have A as the top of the stack, I read the A, again, I push the A that I had so it doesn't get popped, and I push a new A so that we push a new A consequence of reading this input terminal symbol A, yeah? And finally, the last transition in here is that if I have A as the top of the stack, like so, I pop the B, yeah? So here the idea is that I have A as the top of the stack, I read the input symbol B, and I pop the A, right? Which is, this case, the element at the top of the stack of this automata, yeah? We will see with examples how this work, yeah? And then what happens when I start reading B as well? If at first I haven't read anything and I read only one B, then I come to the state B, and if I stop the word, then basically it means that my word will not be accepting, yes? However, if I have the same amount of A's and B's, I come back again to the state S, like so, yeah? And in this state, within this state, we can stack the number of B's we want. We can go stacking B's in a sequential way. So if I have B as the top of the stack and I read the B, then I push the B times the first one is so that the one I had before doesn't get popped, and the new one is the consequence of reading this new symbol A, in this case B, right? So the next transition is basically if I have B as the top of the stack and now I read the A, I have to pop the B. Yes, so it gets unsolved. And this is key to understanding this problem. If I have A as the top of the stack, if I read the B, I have to pop the A. If I have B as the top of the stack and I read the A, I have to pop the B. Yeah, so to understand this, consider this following word. Imagine if I have the word A, B, 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 A. So this word is a valid word because I have the same amount of A's and B's. And this condition then is satisfied. Okay, so this word belongs to the language. How will this input work and execute in my automata? Well, let's see it. Okay, at first what we do, we just read the A, okay, and if we read the A, what we do, we push a new variable a, like we have explained in here, yeah? So basically, it's the transition where I have z as the top of the stack, I read the a, then I push the a. So basically, what will happen is this will get popped, but since we have pushed it again, this will get pushed again, and then we push the a. So, okay. Then when we read the next a, this is the transition where I have a as the top of the stack, yes, and I read the a. So I push the a so it doesn't get popped, and then I push anyway, consequence of reading this a, yeah, like so. Now what happens with the b's? Now keep in mind when I read this b, let's just put it with another color. When I read this b, I have a as the top of the stack, right? I have the a. So the transition that we are considering now, right, is this one. I have a as the top of the stack, and then I read the b. So I pop the a. Yes, is it seen now? We pop the a. So what we basically do, since we have not written any action, remember that if we leave a blank in the action, it means that we don't do anything. So we don't push anything. So by default, the automata, what he will do is basically pop the top element of the stack. So here, when we read the b, this gets popped. And then when we read the second b, this gets popped again, right? So we will just pop it from the stack, like so. Now what happens? Well, now we read the b. Yes, this being here. We read it. But do I have the a as the top of the stack? No, I have the z as the top of the stack. So now the transition that we are considering, which is, well, is this one. Since I have z as the top of the stack and I read the b. So I have to push the b, okay? So then we push a new b in here. Yes? Then when we read the a, this one, what happens? Well, since I have b as the top of the stack and I read the a, I have to pop the b. Yes, so we pop the b. And this is basically the transition that we do in this here. I have b as the top of the stack, I read the a. Keep in mind that in this moment we are in the state b, which is a non-accepting. However, at the end, after reading all the elements from the input, yes, after reading all the symbols, all the elements from the input, we have z as the top of the stack. If we have z as the top of the stack and we are not reading anything, right? We just have z as the top of the stack. There's no more thing to read, yes? Then what will we do? Well, we will just do this transition. So we come back again to the state S, right? Because now we have the same amount of A's and B's. And if this happens, then the condition is met, the condition is fulfilled, and it is satisfied, this one, and then this word that we are considering will be an accepting word, which is in essence what it is, because it belongs to the language L. So we have seen now, after reading all the elements from the input, yes, there's no more input to read, yes, basically, after reading all the elements from the input, we end up in a accepting state, which is the state S. And you can verify that for any given word that belongs to this language, the PDA will accept it so that it will end up its execution after reading all the elements from the word in a accepting state. And in an analogous way, if we have a given word that does not belong to this language, so our PDA mustn't accept it, then it will behave correctly because it won't accept the word. Okay, if we have a word that doesn't belong to the language, then after execution of this word in the automata, okay, we will read all the elements from the word, and then we will end up finally in a state that will not be accepted. In this case, the state B. Yeah, you can verify this. So this is in essence the correct automata for this problem 5. We remind the student that he can check the statement of this problem as well as its solution in the resources of this lesson.